Hi guys, this is lesson 14-1. Alright, the learning target for this lesson is to classify real numbers and tell whether an operation is opened or closed under a set of numbers. Well, that's a lot, and you're probably not sure what open and closed means. Probably not something you've heard of before, and that's fine, we'll get there. Okay, so let's talk about the categories of numbers that we will be using for classifying. Alright, natural numbers, if you think back to like caveman times, if a caveman found rocks or something he was going to count, or animals that he was going to be hunting, those would be the natural numbers. Okay, these are the numbers you think of when you're counting something in nature. These are the counting numbers. When you're a little kid and you're first learning to count, you start with 1. All right, so the counting numbers are like 1, 2, 3, 4, and so on, and 0 is not included in this group. So natural numbers start at 1, count, no 0. Whole numbers, I've got a typo here that I'm going to fix. Whole numbers would be your natural numbers plus 0. So basically the only difference between natural numbers and whole numbers is we're including 0 this time. Okay? Integers would be your positive and negative whole numbers. So now we're adding a layer to this. The layer is now we have 0, we have 1, 2, 3, 4, 5. We're also adding -1, -2, and so on. Okay? Rational numbers is a number that can be converted into a decimal. Now that's how I prefer to think of it, okay? That terminates or repeats. So like fractions, percents, we're going to go over a whole chart that shows rational numbers and what they can be. If you look up the dictionary definition of a rational number, the word rational has the word ratio in it. Okay, and ratio means fraction. And the technical definition of a rational number is something that could be converted into a fraction with whole numbers in the numerator and denominator. But we're going to differentiate between rational numbers and irrational numbers based on how they look as decimals. So that's why I choose to talk about it in terms of decimals. It's a decimal that terminates or repeats. Okay, irrational numbers would be a decimal that never ends, never repeats, like pi or square roots of non-perfect squares. Okay, basically if you do a root and it fills the screen, that would be your non-perfect squares. Okay, that could be cube roots as well. All right, real numbers, real numbers are all the types of numbers that we work with, okay? In algebra, we only deal with real numbers. When you take Algebra 2 Trig, you will learn about imaginary numbers, okay? So the two main categories that we can split up into are rational and irrational, and the Regents likes to ask about rational versus irrational. I know we're not taking the Regents this year, but that's what it likes to ask about. Rational numbers would be like your whole numbers, your natural numbers, your integers, okay? An irrational number would be like pi, okay? Pi would be irrational. If you have a fraction that contains whole numbers or decimals, okay, that would be rational. If your fraction contains a root that would fill the screen, like if you type in square root of 5 by itself, that's going to fill your screen. So putting it over 7 doesn't make it a rational fraction just because it's in fraction form. Okay, that would still be irrational. All percents are rational. Decimals that terminate. Terminate means end. After the 3, there's nothing more after that. It's not repeating. It's not going on forever. Terminate means end after the 3 or after the last number. In this case, it is a 3. Okay, repeating decimals. Now there's a couple different ways you can show repeating decimals. One way would be the part that repeats, you have 3 copies of it. So you have 2, 3, 1, 2, 3, 1, and 2, 3, 1, and then dot, dot, dot. Okay, that's one way of showing repeating, 3 copies and then a dot, dot, dot. We're probably more used to seeing the line over the repeated digits. Okay. The difference would be irrationals would include decimals that go on and on forever, but they don't repeat. They fill the screen on your calculator. Okay? So, for example, 4.13953848. Now, the fact that there's 2 8s in there, that doesn't count as repeating. Okay? Dot, dot, dot. That indicates this decimal does go on forever. 8 is not the last digit, so it's not terminating, it's going on forever, but this is not repeating in any way. Square roots and cube roots that don't fill the screen. For example, the square root of 36 equals 6. So that didn't fill the screen. That makes the square root of 36 rational. However, or in addition, a decimal under the root sign does not automatically mean it's going to be irrational. Okay, root of 0.49 equals 0.7. Okay, so we can still have a terminating decimal to an answer. The opposite of that would make it irrational. Would be a root that fills the screen. So like the square root of 10, for example, would be a root that fills the screen. You're going to get that to be 3 point, a lot of numbers. Okay, off the top of my head, I don't know what it is, but it's going to fill the screen. So that would make it irrational. Okay. This is a really important chart to look at, refer to, and memorize. Okay, the bottom line is if I look at on the irrational side, sometimes it's easier to decide if something is irrational, and if it's not, then it's rational. Okay, pi, irrational. If there's a root that fills the screen, irrational. Okay, the key is if we think about this in terms of decimals, anytime if you convert to a decimal, anytime it fills the screen and does not repeat, that would be irrational. And these are the ways that it can happen. Okay. Okay, so here we're going to take some numbers and we're going to plug them into this Venn diagram. Let me explain, if you're not really remembering what a Venn diagram is, it's you put things inside the circle and the circles can overlap. In this case, the rational numbers nest inside one of another. Natural numbers are rational. Whole numbers are rational. Integers are rational. Okay, and all of these numbers are real. Irrational numbers are their own separate category because there can't be any overlap. So irrational numbers are also real, but they're their own separate category. Okay, so I'll just kind of randomly work this list. Okay, so pi jumps out at me as something that definitely is irrational. We can pull that down and put it into the irrational circle. That's where that goes. Okay, all right. 1.3, that's a decimal. Okay, so it's rational because it's a decimal that terminates. There's no repeating. There's no going on forever. But we can't pull it into the next level of integer because integers can only be numbers without decimals, whole numbers that are positive or negative. So I can only bring it as far as the first layer. Okay, 0. 0 is a rational number. Okay, it's also an integer. It's also a whole number. But I can't bring it into the natural or counting numbers because 0 is not included. So I'm going to leave 0 in this ring. Okay? 2. 2 is rational, but it can go in as an integer. All right? 2 is a whole number. Whole numbers are positive. It's also a natural counting number, so I can pull the 2 in to the topmost category, natural counting numbers. Okay, the CNTG stands for counting numbers. Sometimes natural numbers are called counting numbers. 2/5. 2/5 is a fraction. Remember, the word rational has the word ratio in it. Fractions are ratios. So 2/5 goes in the ring that represents rational numbers. But because it's not any kind of whole number, positive or negative, I can't drag it further into any of the circles. -8. Okay, -8 is rational. It's an integer, but because it's negative, I can't bring it into whole or natural or counting numbers. 2.6, repeating. Okay, so repeating is rational, and I remember that because they start with R. So if I go back to this, R, rational, R, repeating. Okay, that's an important and often missed concept. Rational and repeating. Repeating is rational. Okay, so anytime you have a repeating decimal, like 2.6 repeating, that would be rational. Now, because there's a decimal, I can't bring it into any of the closer rings, so it has to stay in the rational ring. While we're talking about repeating decimals, remember that 3 copies of a number counts as repeating decimals. So 23, 23, 23, ... is repeating. Repeating is rational. So I'll bring it into the rational ring. Okay. 4. Well, 4 is kind of like 2 that we have over here. So 4 is rational, but it's also an integer, but it's also a whole number, and it's a natural or counting number. So I can pull it all the way into this smallest circle. All right, square root of 10, we talked about how square root of 10 would be a calculator, it would fill your calculator screen if you typed it in. So because it has a fill the screen type answer, it is irrational and goes down here in the irrational circle. And we talked about how perfect squares like 25, because that equals 5. All right, so keep in mind, equals 5. Okay, the square root of 25 is rational. Because it's equal to 5, it's also an integer. Because it's equal to 5, it's also can be a whole number. And because it's equal to 5, it can also be a natural or counting number. Square root of 0.25. Well, that also will come out evenly as 0.5. So, because it comes out evenly, does not fill the screen, it is rational. However, since 0.5 is a decimal, I can't bring the 0.25 under the root. I can't bring it into integers, whole numbers, or natural counting numbers. It's got to stay in that ring. Okay, improper fractions, or fractions that have negatives in it. Okay, just based on the fact that this is a fraction with whole numbers in it, makes it rational. Okay, but since negative 12 doesn't divide 5 evenly, the answer would be negative 2.4. No, yes, negative 2.4. That would be a decimal. We can't bring it into the integers ring, so it has to stay in the rational part. And the fact that it's negative really doesn't have anything to do with it. It's the fact that it would divide out to a negative 2.4, and that would be a terminating decimal. All right, I saved this one for last because it tricks people. Okay, so 0.1 22, 333, 4444. So this has a pattern to it. And we talked about how repeating, well, repeating is a pattern also. However, repeating is a very specific type of pattern. And other patterns don't count. So 1, 2, 2, 3, 3, 3, 4, 4, 4, 4 is not rational because although it's a pattern, it is not a repeating pattern. Okay, I don't see 3 copies of the same number 3 times like I do here. 23, 23, 23. Lastly, let's talk about closure. So this is a kind of a weird but easy but difficult concept to wrap your head around. All right, a set of numbers is considered closed under an operation if and only if an operation between those types of numbers produces the same type of number. Okay, let me tell you what I mean by that. Okay, if I have natural numbers, so those numbers starting 1, 2, 3, 4, and so on. If I pick any two natural numbers, and I add them together, could I get a negative number? Okay, so let's say positive 3 and positive 10. Could I add those together? Is there any possible way I could get a negative out of that? Is there any way I could get a decimal out of that? Could I get an irrational number out of that? Okay, so that's what closure means, is if I take any two numbers and perform an operation, addition, subtraction, multiplication, or division, do I get the same kind of number back again, or is there a way I could get a different kind of number? And that would be not closed. So counterexample is when you can think of a example that would make it not closed. So it would be an example that proves a statement is false. All right, so let's get into this because I think it's easier if I demonstrate it to you. So this is a chart that you're going to want to refer to when you do the assignment. All right, natural numbers, remember that is your 1, 2, 3, 4, and so on. Okay, so under addition, like I said, that's closed. That means that if I take any two natural numbers, it doesn't matter what they are, any two natural numbers, and add them together, all I can get back is an natural number. Okay, subtraction. Is it possible to take any of these numbers and subtract and get something that's not a natural number? Well, turns out that's not closed. And CE here stands for counterexample. So 3 is a natural number, 5 is a natural number, but when I subtract 3 take away 5, the answer is -2. Now -2 is an integer. It is not a natural number. So we consider this not closed because there's a way to get numbers that aren't natural when we subtract. Multiplication is closed. If I take any natural numbers and multiply them together, there's no way I can get a decimal or a negative or anything like that. So it's closed. But just like subtraction, division is not closed. 1 and 2 are both natural numbers. But if I divide 1 divided by 2, I get a decimal, and decimals are not natural numbers. Whole numbers and natural numbers, remember the only difference between those is 0. So, because that's really the only difference, it doesn't really change anything. It's the same operations closed and the same operations not closed. Now, I've offered different counterexamples, but it's really the same situation. Okay? Integers, remember that includes your positive and your negative numbers that are whole. So like -2, -1, 0, 1, 2. Okay? Closed. Okay? If you subtract, now see where we had a problem with natural and whole numbers, we could get negative answers. Well, since integers can be negative, that's not a problem anymore. so it's closed. Multiplication is also closed, but division, we can still get decimals with division. 3 divided by 8, 3 and 8 are integers, and if I divide them, I get decimals, so that's not closed. Okay, rational numbers, closed. Subtraction is closed. Multiplication is closed. Division is closed. If I have rational numbers, there's really no way I can get anything but a rational number back again with addition, subtraction, multiplication, or division. I can't somehow take two rational numbers and get an answer on the calculator that goes on and on forever but never repeats. Irrational numbers, let's see, it's not closed for addition because if I take the square root of 5, well, that's irrational. And I take the negative square root of 5, well, that's also irrational. And I add those together, I get 0. Well, 0 is a whole number and an integer, so that's not the same thing. It's not, 0 is not irrational. Okay, so that's why it's not closed. All right, subtraction, also not closed. If I do pi, take away pi, I get 0, and for the same reason that addition didn't work, neither does subtraction. Multiplication is not closed. If you type the square root of 5 into your calculator, it fills the screen. If you type in square root of 20 on your calculator, it fills the screen. But if you multiply root 5 times root 20, you get root 100. And root 100 is 10. 10 is natural, whole, integer, which is, so that's, 10's not irrational, so it's not considered closed. And division is not closed for the exact same reason. If I take two roots and divide them, it's possible that I could get a root that simplifies to a whole number or rational answer. So all the rational numbers are closed and all the irrational numbers are not closed. Real numbers. Real numbers is all our numbers. We are not working with anything besides real numbers, so all of our operations are closed for real numbers. So again, I'd like to stress that this is a chart that you definitely should be looking at to access your assignment and to be able to answer questions on your assignment. Thanks a lot, and see you for the next video.